Okay, so in review question 5, it's the last question on this set of 3 questions related to this PV diagram, where we have an ideal monatomic gas taken from state I to state F through different paths, and this question is related to the path B, the ratio of the work done on the gas along path B to the initial thermal energy of the gas. So the work done on the gas is equal to the negative area under the PV curve. So the area underneath the PV curve for process B is technically area of a rectangle that's got a base. So there's no, let me just try it, so yeah, I'll finish the sentence here. So there's a phi to 5v, so it's a base of 4v's and a height of 5p's, so the area is the absolute value is 20 PV. It's technically a negative area since you're going from a large V to small v, but we know that the work is going to be positive. I'll explain that in a second. So during this isochoric process from I to up to this particular point, there's no work done at all. So sort of as an additional review, no work is done during an isochoric process, no change in volume. Then all the work is done during the isobaric compression. So again, having basically a constant pressure of 5 P's times a base of 4 V's. So, and it is a compressive process, so the work done is positive. So the work on technically is negative 20 PVs. You might find it easier just to figure out the absolute value of the area, just figure out the area just from geometry, and then determine whether it's positive or negative based on whether it's a compressive or a expansive process. So this is going to be 20 PVs, so this is a quick review. I'll write that down here. So work on is positive when Vf is less than Vi, so compression, and work on is negative when Vf is larger than Vi, so during expansion. And the opposite is true for when you're thinking about the work done by the gas, but I tend to focus primarily on the work done on the gas. So the initial thermal energy, so E thermal initial is 3/2 of N or T initial, but this quantity N or Ti is equivalent to Pi times Vi. So E thermal initial should be 3/2 of the initial pressure is P, if initial volume is 5 phi, so it's 5 PVs. So in this particular case, it's 3 times 5 is 15, divided by 2 is 7.5 PVs. Okay. So both are energy terms, so the PV product by definition has to be energy, and correct units will be, if you in pascals times meter cubed will give you a joule. So we're looking for the ratio in this question, the ratio of the work to the initial thermal energy. The work is 20 PVs. The initial thermal energy is 5 PVs, which is also the same as, oops, sorry, I can't see that. So the work is 20 PVs over the initial thermal energy 7.5 PVs, which is also the same as the final thermal energy. So this gives you a ratio about almost 3, so 2.7, which makes C the correct answer. Okay, so I was just thinking as an additional question, if you were asked to draw a first law bar chart for either process B or process A, what would that graph look like? You're welcome to pause the video and to try that. What would the first law bar chart look like? So things that we do know for this process, for both processes, I'll sort of maybe I'll put some red pen here as a separate piece of information. that I know that E thermal initial is equal to E thermal final. That's Pi Vi equals Pf Vf for both processes. The work on is positive because they're both compressive processes, which means that the Q exchanged is negative, and I know that the work on has the same absolute value as Q because delta E thermal is 0. So if you're drawing a first law bar chart, try to draw this reasonably accurately. See if I run out of room here. So I'll make the initial thermal energy pretty small because I know that the work done is about 3 times bigger. So I'll make it pretty small. 2 or 3 mils here on my ruler. So that's my A thermal initial. This will be my A thermal final. It should be the same height. Sorry if I drew a little bit bigger. It should be the same. The work done is positive. And it should be about 3 times bigger than the initial thermal energy and the final thermal energy. And then the Q should be negative at the exact same absolute value. So if we write here that this is E thermal initial plus work plus Q equals E thermal final. So since we both know that the initial thermal energy is the same as the final because we haven't changed the temperature of the gas. Well, the temperature of the gas initially is the same as that as it is at the final state. The working Q must be equal in absolute value, opposite in sign, and this will be the correct first law bar chart for both the entire for process A and for the entire process B.